In this lesson, we're going to go through something that many of you have already seen before. So distance time graphs is our topic today. We're also going to be working through the worksheet as we go, so make sure it's nearby so that you can follow along with it as we go through the video. In case you don't remember, distance time graphs are just used to show how far an object has traveled in a certain amount of time. The time always goes on the x-axis, and then the distance from the starting point is always on the y-axis. A few things we need to know before we actually get started. So first, a straight diagonal line, which we'll see pretty often, shows that an object is moving at a constant speed. Then a horizontal line shows that the object is not moving at all. And then we also need to know the steeper the line, the faster the object is moving. We're now going to look at example 1 from the worksheet. So go ahead and have it nearby, whether that's actually printed or if you didn't print it because you don't have to, then make sure it's on another tab on your browser. We're looking to find how far the car travels in the first 3 seconds. So 3 seconds is going to be from the x-axis because that's where the time is. So we'll go up from the 3 until we hit our line, and then we need to go across to actually read the distance at that time. So we'll see that it's gone 60 meters in the 3 seconds. Part B says how long was the car stationary. Remember, stationary just means it's not moving. And to find out when it's not moving is we look at the horizontal line. Now we actually have to find the difference from the starting of it's not moving to its finish. So it goes from 4 to 6, and that is 2 seconds. Another fact of distance time graphs that we need to know is that the gradient will tell us the speed. We're looking to find the car's greatest speed, so we're going to have to actually find out which one is the steepest line. Looking at it, you can see that that middle diagonal is the steepest line, so that's going to tell us our greatest speed. We'll start by finding the gradient. Remember, the gradient is the change in distance over the change in time. We can see that it goes from 80 to 180 meters, so it goes an increase of 100 meters, and then that takes place in 2 seconds, so it's 100 meters per 2 seconds, or 50 meters per second. Another thing you could be asked is for average speed. That's just the total distance divided by the total time. It includes any stopping moments. But you also need to make sure that you match your units to the units that are presented in the problem. Last part of example 1 is looking for the car's average speeds. Remember, that's going to be total distance. So from 0 up to 220 over the total time of 0 to 10 seconds. So it's 220 over 10, or just 22, and it's meters per second. You also need to know that the further the line goes from the x-axis, the further away the object is from the starting point. This means that if the line goes back towards the x-axis, it's actually returning to its starting point. We're now going to look at example 2 from the worksheet. We're now going to look where a cyclist has a journey that goes from home to the next big city and then returns home. So we want to look at how long the cyclist was stationary during the journey. There's actually 2 points, and we can tell by the horizontal lines. So the first one was for only half an hour. The cyclist's second stop was for an entire hour. So to find out the total time stationary is you just add them together, 0.5 plus the 1 hour, so you have 1.5 hours. To find out the total distance traveled, you'll actually have to first figure out the farthest point of the journey. So this can be done by looking at the highest part of the graph. That's actually at 35. Then he also returned home, so he doubled that. So you will just multiply it by 2 and you get a total distance of 70 miles. To find the speed of the journey home, you're going to look at where the gradient is descending. So we're actually going to be finding what normally would be a negative gradient, but we're actually not going to consider it negative because it's not saying that it's going down in speed, it's just saying it's returning home. We have to find the change in distance, which is 35, over the change in time, which is 2.5. Then we need to simplify 35 over 2.5, and we get 14 miles per hour for the cyclist's speed on his journey home. To figure out the greatest speed, we again need to figure out which one is the steepest line. In this case, it's the second diagonal line that is going up. Then we're going to just figure out the gradient for that. So you can see that it goes up 20 miles and it goes across that in 1 hour. So it's just 20 miles per hour. It'd be a good idea to actually pause the video now and complete questions 1 through 5 on your worksheet. And then once you're done those, you can come back, hit play, and we will go through examples 3 and 4. We're now going to go on to example 3 and 4. These are more drawing distance time graphs rather than actually interpreting them. Now he's going to the gym and then he's going to return back. Right now we can see where he's gone to the gym and then where he's actually at the gym. Part A is saying to figure out the speed of his way to the gym. So remember, speed is just the gradient of our line, so we have to figure out how much it changes in distance over how much it changes in time. You can see that the distance is just 12 kilometers. It goes from 0 to 12. The time, though, is going from 0 to 1 square past the 1, so you do have to make sure that you're reading the scale correctly. In this case, it's 1.25 hours. And then just simplify and you get 9.6 kilometers per hour. In part B, we're actually looking at completing the distance time graph. We're told that he stays at the gym for 75 minutes, which is actually already shown by that horizontal line. And then he's traveling home at 16 kilometers per hour. We want to complete this diagram. We actually have to first figure out how much time will pass in his journey home. We know that speed is the same thing as distance divided by time, so we can actually rearrange that to make time equal to distance divided by speed. Now our distance, we actually have to look at the graph to figure out that it's 12. It's just the tallest part of our graph. And then our speed, we're told, is 16. Simplifying that, 12 divided by 16 just gives us 0.75 hours. So now what we're going to do is we're actually going to put a point on the x-axis, because that's where he's back at home, at 0.75 hours later than the horizontal line's ending point. So remember, that's just going to be 3 squares. The last thing you have to do is just connect the end of the pre-drawn graph that we were given to your point. Make sure you use a ruler. It should actually be a straight line. Let's now move on to example 4. In example 4, we're told that Lucy leaves home at 8 o'clock. She walks at a speed of 4 miles per hour for 15 minutes and then immediately runs at 8 miles per hour for 45 minutes. She stops for half an hour and then sets off home to arrive at 10:45. We're going to be drawing all of these steps. We need to start by actually figuring out the distance covered in her time that she was either walking or running. So let's first figure out what the formula is. We know that speed is normally distance divided by time. If we rearrange that, we get that distance is just the speed multiplied by the time. Looking at when she is walking, she does 4 miles per hour, so we're given our speed, and then for 15 minutes. Now if you notice, in our graph, we're asked to graph it in terms of hours. So we actually need to convert this 15 minutes out of 60 minutes into hours. So it's just a quarter, so it's 0.25 hours. We can find the distance now by multiplying the 4 and the 0.25 to get that she goes 1 mile in her walking time. Then we need to actually draw that in our graph. So we can say quarter mile, which is just 1 square, will go up to 1 mile. Now let's look at the running time. So we have a speed of 8 miles per hour. And then again, we're given 45 minutes. We need to change that to be in terms of the hours. So we'll do 45 divided by 60, and you get that it's 0.75 hours spent running. Again, we're going to find the distance for the running time by just multiplying 8 times 0.75, and we get that he went 6 miles in this time. Now again, we're going to look at 3/4 worth of an hour, so that's 3 squares, and you have to go an additional 6 miles. So not just going up to 6, but an additional 6. Now we're going to draw the part where Lucy has stopped. So remember, if a person is stopped on here, an object's not moving, it means that it's going to be a horizontal line. So we're just going to have a horizontal line that's 2 squares over, because that represents the 30 minutes, that half hour. Last part is to actually draw the journey home. So after this stop, she will go home and she arrives at 10:45. So we actually just have to put a point at 10:45. That will be the 3rd square over from 10 o'clock. Then just connect a line, make sure it's straight, use a ruler. We can now use our graph to actually find Lucy's speed on our way home. Remember that speed is just the gradient of our line. So we will find the change in distance, which is just 7, over the change in time, which is 1.25. When we simplify that, it becomes 5.6 miles per hour. You can now go ahead and use all the information you just learned to complete questions 6 through 8. So I'd pause the video, but do come back after you're done. Remember, you are expected to have all your workings out when you submit your work, as well as mark your work, and you're going to get your answers just after this slide. That's all for this video. If you do have any questions still, then post a comment on Show My Homework, and I will get back to you as soon as I can. Thanks!